Hello everyone, and welcome to our last set of notes for our space science unit. Today we're going to be talking about the star cycle. So your title should be the star cycle, and your essential question is how do stars develop and change over time? As usual, we are doing Cornell notes, so your title and essential question should be up at the top of the page, and the rest of the page should be divided into two columns. The first column, the smaller one, is for your key points, questions, important vocabulary, and things like that. Your larger column is going to be for your notes. At the very end, you do need a summary. And since your notes are being graded, please make sure that all of the parts are present. So let's get started. Now, when we talk about the star cycle, we're talking about the lives of stars. Now, when we say life, or we say that stars are born, or they live, or anything like that, we're talking figuratively, not literally. Stars are not actually living things. They are basically just giant balls of gas. So they're not living, they're not made of cells, they don't do anything that living things do. But they go through a process that is similar to a life cycle. So that's what we're talking about here. Now, some of the parts of this whole process overlap with the process of making a solar system through accretion, which we talked about during our gravity notes. So the first parts of the star cycle, when stars are born, this is the same thing that we talked about again when we discussed accretion in our gravity notes. So there is a little bit of overlap, but we'll go into a little bit more detail about it in these notes. All right, so stars are born, quote unquote, when the contracting gas and dust from a nebula becomes so dense and hot that nuclear fusion starts. We'll talk in a little bit more detail about that in a moment. Now, how long a star lives depends on one thing, and that's the star's mass. Small stars tend to live much longer than larger stars, and the reason has to do with fuel. We'll talk about fuel in a little bit, but you can think of it kind of similar to cars. If someone's got a large truck, you might know that those trucks go through gas much faster. You need to fill up the tank more often. And just because it's so much bigger, it requires more fuel to run. Whereas with a smaller car, you don't need to get gas as often, and it doesn't go through it as quickly. It doesn't need as much to do the same thing that the truck does. So it's very similar with stars. Smaller ones don't need as much fuel, so they tend to live a bit longer because they don't go through their fuel as quickly as the larger ones do. All right. So the beginning of the star cycle. This is where stars are born. So in the picture off to the side, we have what's called a nebula. And a nebula is a very large cloud of dust and gas spread out in a very large volume, so it takes up a lot of space. Now, in the densest part of this nebula, gravity starts to act, and it starts to pull the gas and dust together. And when it does this, it forms what's called a protostar. And what this is a contracting cloud of dust and gas. And this cloud has enough mass to form a star. Now, stars are huge. They're massive. They have a lot of mass to them. So this protostar, this cloud, needs to have enough mass to form a star. Now, again, this is the same as the first step we talked about in accretion in the forming of a solar system. Now, as we talked about in there, the temperature and the pressure increases until hydrogen atoms start to fuse together. Now, this is called nuclear fusion. So nuclear fusion begins at the protostar point, and this is where hydrogen atoms fuse together again. Now, when hydrogen atoms fuse together, they form helium atoms. Now, the way that works has to do with the number of protons, neutrons, and electrons in the individual atoms. Hydrogen atoms have only one proton, one neutron, one electron. Helium has two of each. So when two hydrogen atoms come together, you now have an atom that has two protons, two neutrons, two electrons. That's what helium is. Two protons, two neutrons, two electrons. Now, when nuclear fusion happens, it releases a ton of energy. And the way it releases that energy is in the form of light. So this is how we see stars burning from many, many, many light years away. We are able to see that light because it's that much energy being given off through nuclear fusion. Excuse me. All right. So the stars use their atoms as fuel. Now, they only have so many hydrogen atoms that they can fuse together to form helium atoms. So those atoms are used as fuel. When the star starts to run out of fuel, or starts to run out of hydrogen atoms, the core of the star, so the center of it, starts to shrink, and the outer portion of it expands. Now, what happens next depends on the star's mass. In smaller stars with less mass, so your low mass stars, what's going to happen is it's going to become a red giant. Now, in that top picture on the screen, you see a red giant compared to our sun. Now, our sun is in a part of the life cycle that we call main sequence. This is where the star is just doing its thing. It hasn't started running out of fuel, so it hasn't started this part of the cycle. Now, hang on, I lost my spot for a second. Okay, so when the outer portion expands, with low mass stars, it expands into a red giant. And this is basically just a very large star that happens to be a red color. Now, eventually, over time, the outer parts of the star grow larger and they drift off into space. And this forms what we call a planetary nebula. And that's what you see in the middle picture. So that middle picture, it is a real picture. That's actually what they look like. So it's very cool looking. You can see the red. That's the same stuff that's giving the red giant its color. It's the same gases. So this is just a huge cloud of very, very hot gases that have drifted apart. It was once a star, and the outer portion of that star is just drifting away. Now, in the center of that planetary nebula is the core of the original star. And that core becomes what we call a white dwarf, which is a very small star. Now, in the bottom picture, there's actually two stars there. One of them is a white dwarf, and that's the one that's in that white circle with the arrows pointing to it. So that itty-bitty little spot, that's a white dwarf. So they're very small stars, and again, this was originally the core of the star that is basically dying. So this is at the center of the planetary nebula. Now, over time, the star cools down, the temperature drops, and that's because it's running out of fuel. Now, once it runs out of fuel, the star cools down and it stops glowing. And when it gets to that point, we call it a black dwarf. And we call it that because it's not glowing. It's not giving off any light. It doesn't have any more fuel to do that. So we when they actually become a black dwarf, we can't see it because it doesn't give off any light, so it's completely black. Right. Now, medium and high mass stars, when they, and these are larger stars, when they start to run out of fuel, again, the core shrinks and the outer portion expands. Now, these are larger stars. They have more mass. So they don't become giants, but they become supergiants. So these are much bigger stars. And actually, in the picture below, you can see a blue giant star. And if you notice, it says that it's 864 million miles across. And there's a diagram of our solar system, and that large oval you see is actually Jupiter's orbit. So this supergiant star is almost as big as Jupiter's orbit, which is absolutely huge. Now, when the supergiant runs out of fuel, it explodes. And we call that explosion a supernova. And that's the top picture on the side. And again, that's an actual picture. That's what it actually looks like. That's just an explosion of gas. So that big cloud was once a star. Now, from there, a medium mass star, and that's the picture right off to the side, the material left behind from the supernova forms a very small, very dense star that we call a neutron star. And in that picture, you can see a supernova, so you see all that gas from the supernova, and that speck you see in the center, that's in that square, that is the neutron star. So that was once the core of the original star. So now it's very small, it's very dense. Now, the biggest stars, the ones with the most mass, they become black holes after the supernova. Now, black holes are objects that have so much gravity that nothing can escape them. So in order to become a black hole, it has to be enormous, with so much mass that it has way more gravity than anything else around. And we actually can't see black holes. Scientists haven't been able to photograph them, even with all the technology we have. And the reason why is because it sucks in light. Not even light can escape its gravity. And the way we see things and the way we're able to photograph things all deals with light and the reflection of light and light being given off. So if something is sucking light in, we actually can't see it. So that in my opinion is pretty cool. But that's just me. All right. So this is a diagram of what happens. I would recommend writing this down. I'm going to say definitely include this diagram in your notes so that you can refer back to it. And that is it. Now all you need to do is write your summary. And you're done.